This is the first lab, the first official lab, the first hands-on lab. So with that, you need to have proper safety. Really quick, here's the, you guys have your materials out and ready? So yeah, uh, when you click on the first lab, our, I'll show you where to find it here under lab exercises, under the modules. It's laboratory techniques and measurements. So I tasked you guys with doing this first tab, exploration, over the weekend. I hope you did that as well. And now we're here under experimentation. So quick learning objectives are on the bottom. We're basically going to be learning how to do some of the stuff you guys know how to do this already, like converting or converting from like centimeters to meters or Celsius to Kelvin, etc. So there's a materials list here. A lot of the student supplied stuff is simple stuff that you can find in your home. Um, the lab is due Monday at 11:59 p.m. So there's no need to feel rushed. I believe Angelia, the other tutor in the class, she has a lab session this Saturday, I believe. I don't know the exact time. And Dr. Henry also has one on Monday, this upcoming Monday. And they'll both be doing this lab as well. So just a heads up. So uh let's get started. So does everyone have their materials out in front of them? All right. If not, I'll give you a minute or two to get everything. So we'll wait here for a couple minutes. And let me know when you guys are ready to go. Just a quick reminder, this lab is decently long. Dr. Henry told me it took him about 3 hours. Again, you're more than welcome to work at your own pace if you want. Um, I You don't want to be handheld through the entire thing. I get it. Also, you're more than welcome to do it on your own time as well. I'm here just simply as more or less a guide for those who need it. All right. Uh, let's get started on this first part. So in this first part, we're going to be taking a look at measurements. So here it says gather a metric ruler, CD or DVD, key, spoon, and a fork. So I hope everyone has one of these things in front of them right now. I don't have a CD or a DVD. I I live in the current year where everything's digital, so I had to find something as a replacement. I don't do that. Please use a CD because it would mess up your data. So for now, I'm just gonna be using a key. So here on note three or step three, it says measure the length of each of the following objects, the ones I listed below above, with the ruler in centimeters to the correct level of precision and record the data on table one. So the data table one, and here are the tables that we're going to fill out. So it looks like in this first part, we are just going to be filling out these boxes with the data. So I'm doing key first. And it looks like my key is about 5.1 centimeters. So I'll annotate that. So 5.1. And on the instructions, it says convert measurements for each of the objects from centimeters to millimeters. So we have to do some simple conversions. I'm sure you guys are pretty good at this now. So if you don't know off the top of your head from centimeters to millimeters, that's fine. I don't. In the packet that you were allowed to use for the exam, there is a table full of conversions. So you're more than welcome to use that. But we do know that for 1 centimeter, it is equal to 10 millimeters. So if we take our given, which is the 5.1 that I measured, that is our starting point. And we know we want millimeters. So in this conversion, um, what's going to go on top and what's going to go on bottom? What do you guys think? So because we want millimeters and we're with centimeters, we want to get rid of centimeters. So that's going to go on the bottom, and on top are millimeters. And now that we're on the units that we want, we just do some simple math. And we should get, oop, that's not right. 51 millimeters. So I'm going to put that on the second row. And here on the next step, it says convert millimeters to meters. So we're doing yet another conversion. So this is our new starting point here, the millimeters. And we know based off our conversion sheet that 1 meter is equal to roughly 1,000 millimeters. So our new starting point, 51. And then we want to get to meters. So our 1,000 is on the bottom and meters on top. The units cancel. Giving us 0.051 meters. And that's going to go on this third row. So pretty simple math. You guys have any questions? Okay. So yeah, we're basically doing this process for CD, a key, spoon, and a fork. So let's all take a minute to do those measurements out. All right. So that's what my table looks like. Again, I don't have a CD, so I don't think a hard drive would suffice. It's a good data point. Okay. I'll give you guys a few more minutes to fill out your table. All right. Let's move on to part two. I'm gonna clear my screen. All right. So now we're doing temperature measurements. So here we're gonna be using a 100 milliliter glass beaker, a cup, a match or lighter, a burner stand, burner fuel, thermometer, and a 2 ounce aluminum cup and an aluminum pie pan. So let's gather all that. Okay, let's see. Yeah, they gave me the most weird looking thermometer. It's almost hard to read the measurements. So it'll do. Okay. Uh, Here on step 8 of part 2, it says turn on tap water to hot and let the water run as hot as possible for about 15 seconds. So then you're going to take your 100 milliliter glass beaker and fill it to about 75 with the hot water. And then you're going to measure it with your thermometer and put the data on table 2. So this one. So does everyone have access to running water or hot water? Okay, good. Uh, I'm gonna go to my kitchen and do this step. So let's all take a minute to get hot water. All right, I'm back with hot water, and then now we're just gonna take the temperature. So it looks like the highest point for me was 42 degrees Celsius. So that's where that's going. And it looks like we're going to be converting to Fahrenheit and Kelvin here shortly. All right. So let's see what our next step is. So looks like we're going to be using safety glasses. And looks like we're going to be using the burner fuel. So since we're working with fire, everyone, make sure you're in an area that is safe for you to do so. Um, I'm in my room currently and trying to set a good example. So I'm not sure if I should be lighting things on fire in here. Um, so are the rest of you in a good area to have a fire going? All right, let's move on. So let's see here. Assemble the burner setup and light the fuel. So you have a aluminum pie plate as your base, and you're gonna set the burner stand towards the back of the plate. And okay, yeah, this is how the setup is gonna be. So if you have the side open and you scroll down to figure 14, it shows how the setup's gonna be for the next few steps. So let's do that. Okay. So does everyone have a flame going? All right. So I opened my window because I'm right next to it. You guys hear cars and whatnot, just ignore it. All right. Now I'm letting the water boil. So this might take a minute. Yeah, I can see my temperature rising quite a bit. There should be a thermometer in your kit. It's I believe it's in one of the boxes, like the skinny boxes, and it's like the color yellow. At least mine was. Okay, that's fine. Have a good day, Akita. So I'm about at 61 degrees Celsius. So once it reaches a full boil, you're gonna let it continue for about 5 minutes, it says. Oh, Adriana said that hers was in a box in box two, bag A. I don't know if you saw that. Since I'm right on the window, I feel like my neighbors think I'm up to something devious at the moment. So I think while this continues to heat up, um if you guys have access to ice, go ahead and grab that for now, as we're gonna be using it shortly after the boiling step. Okay, so mine's full boiling now. So I recorded this a little too early. 95. So now I'm gonna wait 5 minutes and see what it is. So, in the meantime, I'm gonna go get some ice. All right. Does anyone have any questions so far? Is it pretty straightforward so far? So looks like mine after 5 minutes, it's leveling out to about 98 degrees Celsius. Okay. So are we on the same page, more or less? Okay. So let's continue on. It says use a small 2-ounce aluminum cup. So it's this thing right here. To extinguish the burner fuel flame. Do not touch the metal stand or the beaker because they're hot. Carefully slide out the fuel canister from underneath the burner stand. Put the aluminum cup directly over the flame to smother it. And then we're gonna allow it to cool down. So, uh, I just put the cup on top of the burner fuel, and now I'm just letting it cool down for now. So it says once all equipment is completely cool, remove the aluminum cup and place the plastic cap back on the burner fuel. Weird. Mine didn't have a plastic cap. Ensure that the plastic cap snaps into. Oh, I think it's talking about the lid. I'm dumb. Uh, Make sure it snaps into place to prevent fuel leakage and evaporation. Uh, this is because a lot of this stuff is going to be used in future experiments. So let's take a minute to do that. So, if you're wondering when your beaker is cooled down, don't grab it. Please don't grab it. Just more or less hover your hand near it so you can feel the heat. All right. So while that cools down, let's read on ahead. It says, well, to let the beaker cool down, obviously. Turn on the tap water this time to cold and let it run as cold as possible for 15 seconds. So then we're going to use a cup, plastic of drinking, about halfway full of that cold water. And then we're going to do the same steps of measuring its temperature as we did with the boiling water. This time, though, we're going to be using ice cubes. So allow the ice cubes to sit for approximately 1 minute, then record your data. And then after 5 minutes, we're going to record the temperature again. So I'm going to go grab cold tap water so we can fill up the next few boxes. All right, I grabbed my water, my cold tap water, as cold as it'll ever be. It feels more like lukewarm, if I'm being honest. And now I'm gonna take its temperature. So looks like my thermostat dropped from a 98 degrees Celsius when it was at its peak boiling to about 18. So pretty drastic change. So now that I have that, I'm gonna grab the ice cubes and just pour it into the tap water and see what my data is from there. Oh, that's pretty funny. My my ice cubes froze on my cup. They won't come out. That's actually hilarious. I guess I'm just gonna pour it onto. All right, 1 minute. So my temperature dropped about 10 degrees. I'm getting a reading of 7 degrees Celsius. So now we're gonna do the same, just wait more and remeasure after 5 minutes. So is everyone going at the same pace as I am, or is everyone all over the place? Is anyone working ahead? Okay. All right, 5 minutes passed. Looks like I got more or less the same, 5 degrees Celsius. Okay, we have our whole first row done. So that puts us at number 26. So now we're going to be converting our 6 data points from Celsius to Fahrenheit and from Fahrenheit to Kelvin. I believe this is an exam question. At least it was in the practice exam, if I'm not mistaken. So do you guys remember how to do this conversion? So to get from Celsius to Fahrenheit, we're going to be using the equation. I believe it's 9 over 5. That's a 9. Times our Celsius. And then we just add 32. And that'll get us Fahrenheit. So for my first data point, it'll be about 107.6 degrees Fahrenheit. So everyone knows where I got that number, right? And now to get to Kelvin, Kelvin's a lot easier. Um, it's just as simple as taking your Celsius and adding 273.15, and that'll get you Kelvin. So my hot water from the tap is going to be about 315 Kelvin. So pretty easy. We're going to be doing this for the rest of the data points. So let's take what, 5 minutes to do this? That's enough. All right. That's how my data looks like. You guys a few more minutes to do yours. All right, everyone ready to get to the next part? So I'm gonna clear this. Now we're gonna be doing mass measurements. So we need a pen or pencil, 5 pennies, 3 quarters, 4 dimes, and a key. And we're also going to be using our digital scale for this one. All right. So turn on the scale by pressing the power and T button. Interesting. Mine isn't turning on. Is your guys' scale turning on? Let's see. Okay. So the batteries inside the scale are still wrapped. So take off the plastic wrap on them and the scale should work now. And we're going to be make sure the scale is reading in grams. by reading the letter G on the corner of the scale. If there's if the G is not showing, press the M button until the scale reads grams. It says review the different objects listed in table 3. So a much bigger table this time. So estimate the masses for each of the objects in grams and record the data table. Record in data table 3. To help you with this process, a penny has a mass approximately 2.5 grams. Wait, is that real? Oh yeah, it is. 2.5, exactly. Place a pen or pencil on the scale. Oh wait, I'm reading ahead. So after the penny mass, we're going to tare the scale by pressing T. And now it just reads 0. So does everyone understand how to tare the scale? All right. Place a pen or pencil on the scale to measure the mass. So let's do that. So shockingly, I don't have a pen or pencil on me. It's kind of weird to say as a college student. So I'm going to be using my Apple Pencil instead. All right. So mine reads at 17.89 grams. Oh, actual mass. That's weird looking 8. Repeat the steps 33 and 34 for the remaining objects. So it's interesting that it only wants grams here. Or, I mean, doesn't want anything unestimated. Oh, we were supposed to estimate the masses. I'm just reading too way ahead. So, uh, yeah, for this first row, just estimate what each of these is going to weigh and then record the actual mass. So don't do what I did. This is what happens when you don't read instructions clearly. So if we know 1 penny is 2.5, 3 pennies should be 7.5. In theory, of course, theory only takes you so far. I was roughly right. The actual mass was 7.52. So now I want 1/4. These feel about the same. I'll do 8. Uh, they're not about the same. It wants 2 quarters and 3 dimes. Two quarters, 3 dimes. All right. So 1 quarter is 5.72. So I'm gonna guess like 12. Guess I'm not a good guesser because it's 18.24. So 4 dimes, 5 pennies. So 2 quarters is about 10, which gives, which means 3 dimes is about 8 grams. Hmm. I'm gonna say maybe 20 grams. That's a 2. That's there you go. All right. So 3 quarters, 1 dime, 5 pennies. Okay. 3 quarters. So like 15. A dime. Say 1. So 36 would be my final guess. And the actual mass is 31.87. Now, a key. This feels like 2 quarters. I'm gonna say about 10 grams. Oh, actual is 7.38. Now I want key, a quarter, and 4 pennies. No, 4 pennies is about 10 grams. 1/4 is about 15. And a key is about 7. 23? 24. It's 23.09. So that was pretty close. All right. Who even carries change like that anymore? All right. So I'll give you guys a few more minutes. All right. So now that we have our table, it wants us to convert our actual mass from grams to kilograms. So you guys should be experts at this. So we know our starting point is grams, and we want to finish in kilograms. So when we convert, grams will go on bottom, kilograms on top. So how many grams equate to kilograms? Do you guys know? Do you guys remember? No, it's 1,000 grams is 1 kilogram. So do this quick conversion. We get 1789, 0.01789. So now let's do this conversion for the rest of them. Okay, I'll give you guys a few minutes to do your conversions. All right, I'm gonna clear this. All right, so exercise one, question one. So water boils at 100 degrees Celsius at sea level. So if the water in this experiment did not boil at 100, uh, what could be the reason? So some food for thought. What do you think is making your water boil at a different temperature than it is at sea level? What is sea level? I guess I should say. Do you guys know? So we use sea level as a form of it's a form of measurement to see how high in elevation you are in or wherever you live. So I think oftentimes you'll see sea level put like on a map. Like if you I think if you open the weather map or the weather app, I mean, it'll tell you some form of measurement uh of sea level from where you are. So like Kalinga is I believe at a lower sea level than where I'm from, Fireball. So you get a difference in like pressure, temperature. I think winds are affected as well. So so if 100 degrees Celsius is when water boils at sea level, how would what would be the reason as to maybe why yours didn't at exactly 100? So I'll let you guys write down write down your thoughts onto the box. And again, if this is due on Monday, 11:59. So I believe you can save and come back to it. And remember to be taking like a photo or video to show that you are doing the lab. Okay. Does anyone want to share what they put? Their reasoning behind their madness? Okay. Question two. It says, while heating two different samples of water at sea level, one boils at 102 degrees Celsius and the other at 99.2 Celsius. Calculate the percent error for each sample with a theoretical 100 degrees Celsius. So percent error. Was this on the exam as well? I think something similar was at least in the homework. So what do we know about percent error? Do we know what percent error is? I should start with that. So to calculate percent error, we are taking our measured and subtracting it by the real. And this goes over measured or real. What goes on the bottom? It's real. And then it wants percent error, so that we multiply it by 100. So this is used to show how how much of an error is calculated in your data. Or another way of looking at it is how far off are you from your in theory real point? Because you're never going to be 100% accurate. So we use percent error to see as a basis of how far off you are. So when the question asks, we have two samples here, one, two, and we have a theoretical of 100. So a third number. Which one's going to be our real? – 100. So theoretical and real, those two words can be used interchangeably. So keep that in mind. So our theoretical here, or our real, is 100 degrees Celsius. and it wants us to calculate the percent error for both samples. So we're gonna get two separate answers. So we have our first one here, and I'll let you guys work on them. And remember that your answer is in percent. All right, let's move on. I'm gonna clear the page. So, exercise 2. So, volume and density measurements, part 1. So, let's get our graduated cylinder. $25 mils. Distilled water, a short stem pipette, and isopropyl alcohol. So I'm gonna go grab the alcohol. So I don't think it matters what percentage the alcohol is. Mine's 70. So distilled water and short stem pipette. So if you don't know what a short stem pipette is, um, in one of the bags, it kind of looks like that. Oh, that's a really poor drawing. Don't remember what bag it was on. Uh, if all else fails, you could just look up what it looks like and look for it in your bag. So let's move on ahead. So it wants us to record the mass of the graduated cylinder. table 4. Okay. So assuming all of them should be the same mass. That's how much mine weighs. Let's fill a graduated cylinder with 5 mils of distilled water by using the short stem pipette to add water dropwise until the meniscus is in the graduated cylinder that reads 5. So what it means by meniscus, oh, that's really bad. So when you add liquid onto the graduated cylinder, it's not going to be a straight line. You'll notice that the liquid actually curves like this. So it wants you to read it when that curve is roughly at, was it 5 milliliters? And the reason why you want to use the pipette is because it'll actually let you get closer to that line without the worry of overshooting or undershooting. All right, so let's do this. I have my water here. Now I'm just gonna keep adding. So with the short stem pipettes, make sure you squeeze the bulb before before dipping it into the water. So once the stem's in the water, just let go of the bulb and it'll suck the water in. So don't squeeze the bulb when it's in the water, as it's just gonna make bubbles, and we don't want that. All right, I reached the meniscus, and it wants me to record the volume. So it's about 5. It's not the most accurate graduated cylinder, but it'll do. Now it wants us to place it onto the mass. I mean the scale and record the mass. So make sure you guys are pressing T before weighing. That way it's tiered. And now we're at 22.91. So now we want to calculate the mass by subtracting mass A, this first one, from mass B. And that'll get us our data point for the fourth box. So I got a mass of 4.91 grams. Which makes sense, considering I'm not sure if Dr. Henry mentioned this, but water is the density of water is 1 gram per milliliter. We measured 5 milliliters and we got about 5 grams in mass. So that weighs true. Oh, it says it right here too. So now throw the water away and make sure the cylinder is fully dried. And we're going to do the same steps, but with alcohol. Okay. So this value shouldn't change. Now we're going to do the same with alcohol. I'm like barely short of 5. So I'm going to put 4.9 because I feel like if I add another drop, it's gonna overshoot. All right, so just like last time, we're gonna weigh the cylinder. Then we have our mass. And now we're gonna do the same thing and subtract to get the actual mass of our volume. And 4.12. So now it wants us to calculate the densities of both water and isopropyl alcohol. So who remembers what density is? What is the formula for density? DMV? Does that ring a bell? So density is equal to mass over volume. So it wants us to use the mass that we were calculating, this one, and the volume we measured. So for me, in terms of water, my formula or my equation, I mean, is this. Which gives me a density of about almost 198 point 982, which tracks with the density of water being 1. So now I'm going to do the density of my alcohol. This is grams per milliliters. These are units. So those are my measured densities. So now it wants us to calculate percent error. So exactly how we did with the ocean, ocean temperature or sea level temperatures from the last page, we're going to be doing the same here. So our theoreticals are for water is 1 gram per milliliter. For alcohol, it's 0.786 grams per milliliter. So for water, we take our measured. Mine was 0.982 minus our theoretical, which is 1, over our theoretical, which is the same, 1, and multiply it by 100. So I get a percent error of about oh, I see what I did wrong. I put 100 instead of 1. Percent error of about 1.8%. I'll put that there. And then let's do alcohol. So my alcohol is about a 5% error. 5.09%. So in theory, we want percent error to be as small as possible. Uh, Smaller it is, the closer you are to our real value. The larger it is, the further you are. So when doing lab and you get a ridiculously big percent error, um, that could be because of a bunch of things. If it's very big, it's most likely human error, as in there was a mistake done during your lab itself, or it could have been done during your calculations. So you want it to be as small as possible. And it's never going to be zero. Um, the reason that is because even the equipment we use uh has uncertainties to prevent you from getting 0% error. So I'm gonna clear some of this stuff up so we can move on. All right, part two. Gather a metal bolt, string magnet, beaker, a metric ruler, and a scale. Oh, and a graduated cylinder. So I believe in the materials list it asks for the 1 meter string. Right. I'm gonna clear the data table. And let's see. So we gathered everything that we needed. So I think we're going to be using the same beaker we used earlier from the flame. It should be cooled down by now. So just dump the water that was in there. Make sure it's dried out. Yeah, you want it to be dried out because you never want to measure whether it's a beaker or a cylinder. You never want to measure it when it's like wet or if there's like residue inside. That's because the scale is going to also be measuring the the leftover residue and it will mess up your data. So when you dump the water out, just dry it with like a paper towel or napkin. That way it doesn't mess with any of your results. So let's see. Make sure our scale is tailored, which it should be, as it reads 0. And you're just going to put a magnet on the scale. And we're going to be using 205. So my magnet reads at 4.31 grams. And now we're going to get a ruler, measure the length, width, and height of the magnet. And we're going to be using centimeters. So everyone knows length, width, and height, right? So let's see. So my length comes out to about 2.5 centimeters. The width, about 0.5. And the height, it's roughly the same. Interesting. And now we're going to be calculating the volume of the magnet by multiplying length by width by height. So volume is length times width times height. So we have a volume of 0.625. Now we get to calculate density. So remember, density is mass over volume. So in this case, cubic centimeters is a form of volume. I believe it's because of It's a measurement of in 3 dimension. So we're able to use the same formula for density. So we have our mass and our volume. And it gives me a density of 6.90 grams per centimeters cubed. All right. Does everyone, does anyone have any questions so far? Am I going too fast? All right, let's move on to the next water displacement method. So again, we're going to tear our scale and place a magnet on the scale and measure the object again and record on table 6. 4.53 grams. And now we're going to take our graduated cylinder and put about 6 to 8 mils of distilled water. So where's our pipette? So I'm doing that now. Right? So I got about, what does that read? About 7.5. 7.5 mils. So now that we have that measurement, we're gonna slide the magnet inside the cylinder. Don't drop it in there like I just did. And then we're gonna read. Read where it lies. So the water went up to about 9. I'll say that's 3 mils. 9.3 mils. So now we're gonna determine the volume of our magnet by subtracting the final and initial. So for me, it was 9.3. It's my final. My initial volume was 7.5. So I get about 1.8 mils. Now we want to carefully pour the water from the cylinder down the drain and collect our magnet. And then after that, we're going to do the same steps, but with the metal bolt. So let's do that. Okay. So my metal bolt weighs to roughly 7.34. I'm going to add water to the cylinder again. So this time I actually got about 6.9 mils. So now I'm going to slide the metal bolt down the cylinder. Make sure you're sliding because if you let it drop, water will splash out, ruining your data. It looks like about 8.1. So now we take the final minus initial. Now I'm gonna calculate density again for both of these. So we're gonna take our mass and our volume to calculate density. So remember DMV. And that's grams per milliliters. All right. Got a couple questions up ahead. So I'm gonna clear this table. How much time do we have? We have about 30 minutes left of lab. So in the case that we don't finish during this lab period, you guys will have to just finish the rest on your own. But everything right now seems pretty straightforward. Nothing you guys couldn't handle. So let's see. Questions. Do you guys have questions? Is everyone getting everything so far? It's all pretty straightforward. Okay. So let's see. Question one. An unknown rectangular substance measures at 3.60 centimeters high, 4.21 centimeters long, and 1.71 centimeters wide. And with a mass of 21.3 grams. So what is a substance density? So this is actually something very similar to what we did like 5-10 minutes ago. So earlier we took the length, width, and height of our magnet, which gave us our volume in terms of centimeters cubed. So in this question, it gives us our measured values, and we could use this. We would multiply the three values to get us our centimeters cubed, our volume. So when we do that, we have our volume and we have our mass. From there, we just plug in. So I'm gonna put X here for our volume, as I want you guys to work on this one on your own. And then we have our mass. That'll give us density. So pretty straightforward question, a retread of what we did. And then let's look at our second question. It says we have a sample of gold that weighs 2.615 grams with a theoretical density of 19.30 grams per milliliters. What is the volume of our gold sample? So we have mass and density this time. So if we take a look at our equation for density, our formula, it's density times mass over volume. In this case, we have mass as it's given, 2.615, and we have density, 19.30. So we don't know volume. How would we work for volume? How would we work this equation out? So we would use simple algebra to rearrange our question. Oops. So we want to set it to volume, equal to volume. So all we're going to do is multiply mass on both sides. This causes a mass to cancel out here, giving us our new equation. Volume is equal to mass times density. So we have mass, we have density. So from here, it's just a simple plug in and multiply. Does that make sense? Now for our third question. Oops. A student is given an unknown metal. The student determined that the mass of the metal is 30.2 grams. The student placed the metal in the graduated cylinder filled with 20 milliliters of water, and the metal increased the volume of water to 22.90. Calculate the density of the metal determine the identity of the metal using the table below. So this is pretty close to how we did the last section of this page, where we were using the magnet and the metal bolt. So here, let's take a look at what we're given. So 20 mils of water. So that's our initial volume. And when we put the metal inside, it increased to 22.9. That's our final. So we want the actual amount of volume displaced by the metal. So we'll do that by taking our final minus the initial. That'll get us volume. So we have volume now. We were given mass. as a student waited out in the beginning, and now it wants us to find density. So again, density, mass, or volume. So once you solve this, you solve the density. Choose which of the metal in the chart best represents the density that you got. It's not going to be exact. There's going to be like, you're going to be a little off in terms of like your decimals, but just choose the closest one to your final answer and just write it in the box below. So does everyone get this third one? Now remember, take our final and our initial to get our volume. And then now with that volume in our given mass, we find density. All right. Next page. Concentration, solution, and dilution. So here we're going to need volumetric flask, distilled water, graduated pipette, pipette bulb, sugar, scale, a glass beaker, a cup, scissors, and a sheet of white paper. Okay. So I think we can finish this one in time. Hopefully. Okay. So you guys know what a volumetric flask looks like? Yeah, it looks about right. So let's place this dry flask on the scale, determine the mass. On table 8. So 23.56. So now we're gonna cut a small square of white paper, fold it in half, then in quarters, place it on the scale. So like this. So once the paper is on the scale, make sure to tear it again. That way it reads 0. And then put about 8 grams of sugar on the paper. So let me grab my sugar. I think for this part, it'd probably be best to use like a tiny spoon. That way you don't make a mess. Remember, it doesn't have to be exactly 8, as long as you're close to 8. Darn, I put 9. Um, let's see. 8.57. I think that's fine. Uh, actually, I think I'm gonna just put a little bit closer to 8. 8.18. Okay, that's a lot better. And we're gonna put this sugar inside the flask. Hmm. I wonder why they didn't ask for or even bother putting a funnel in the box. That's fine. So hopefully you guys don't make a mess. Yeah, how is this supposed to work? Almost got all of it in. Yeah, I somehow managed to get it all in there. And then we're gonna add 15 mils of distilled water. So what I would do is measure 15 mils in your graduated cylinder, and once that's there, add add it to the flask. All right, I got 15 mils. Now I'm just gonna transfer it onto the flask. Hopefully not make a mess. So just pour slowly. All right, water's inside. And now we're just gonna swirl the flask until it fully dissolves. So this actually might take a minute. All right, so mine's just about done dissolving. but for the sake of time, I'm gonna read ahead just a little. Okay, so once yours is fully dissolved, use the pipette to add an additional amount of water till it reaches the 25 mil mark. So what it means is, how could I zoom in? Okay, it's kind of hard to see in this photo, but 25 mil mark is this line right here. So if you look at your flask, you see that there's a line. It almost looks like a stain. Um, that's what it means by reaching the 25 mil mark. And you have to be careful on this part because we're working with solutions and dilutions. Um, if you go over that mark, um, you cannot remove water from the flask as the water put inside the flask is already taken into account when it comes to your solution. So what I recommend is as soon as you get near that line, start uh, adding water by drops. So yeah, so add water once it's fully dissolved up into this line. And as you get close to it, just do it by drop. And that way you don't overshoot and it messes up your solution concentration. So let's see. Oops. I didn't want to do that. So once you get to that mark, you're gonna record the amount of sugar, I mean, the amount of volume. So my mass of sugar was about 8.19 grams. And then the volume is however much is the total volume we used inside the flask. And then to get concentration, we are simply dividing the mass of our sugar over the total volume that we used, and we multiply it by 100. So for me, it would be to about 25 mils. It's not going to be exact. Gives me a concentration of 32% or 32.8%. Let's see, table 9. So I'm just going to read ahead a little more. Let's record the concentration of the sugar solution in 3 places. And table 8 for concentration, and table 9 for final concentration in the solution 0 row, and in table 9 under initial concentration in the solution 1 row. So place the flask onto the scale. Uh, and we will get this recording here from step 15. Subtract the mass of the dry empty volumetric flask from table 8. And the flask contains a solution, so this one over here. And the difference of the mass, the difference is the mass of the sugar. Oh, okay. I get it. So we're going to be taking this one and subtracting it to what it reads right now on the scale. And with that, we are given the mass. Since we know our mass and we know our volume, we can find density. And it looks like we're just about out of time. So it looks like the rest of the page is going to be done on your guys' own. If you have questions, please feel free to email me. Reminder, Dr. Henry has a lab session on Monday, so you can go to them as well if you still need help. The lab is due on Monday at 11:59 p.m. So don't put it off to the last minute. With that being said, do you guys have any questions?